Alright, so we're discussing the stress-strain curve, and we are conceptually at this point preferring the idealized stress-strain curve. And our idealized stress-strain curve is something that looks like this. Now, what we've said is that this is a prototypical stress-strain curve, probably has to do with a metal. I have not drawn a distinct yield point, but I could idealize that as well. There's an elastic portion followed by a plastic portion. It's probably a ductile metal. So there are a number of concepts that or terms that you will come across when you read about metallic behavior in particular, but also polymeric if it's a polymer that displays plastic behavior. And these concepts are strength, ductility, and toughness. Now, let me stick to the ideal curve to some extent, but here draw a number of stress-strain curves that eventually help us make a point. Okay, so first one is going to be our ideal stress-strain curve. Okay, so now the three concepts, the strength, the ductility, and toughness, all have to do with the stress-strain curve. Now, the strength is easy. Well, it might refer to the yield strength or the ultimate strength of the material, but let's say that it is eventually and more practically relevant for the ultimate strength. The ductility is associated with the fracture strain. Okay, that's our fracture strain. And toughness has to do with the area under that curve. Okay, so the area under the curve is associated with the integral sigma d epsilon, right? If this was a function, right, f of x, right, the area under the curve would be f dx. Now, when you look at this quantity, you have load over area, elongation over initial length, or by factoring out the constants load over area, let me take the area out, elongation over initial length, let me take the initial length out. So what you have is an integral of load multiplying elongation, integrated over the whole elongation. So load times distance, so that's like work. So this is the total amount of work that is being absorbed in the material starting from the initial loading all the way up to failure. So one says that when that area is larger, the material is tougher. So tougher, it can absorb more energy to failure. Ductile, if it's more ductile, it has a larger amount of fracture strain. It can elongate more to failure. And strength, if you say that the material is stronger, it means simply that the load that you need to apply to break the material apart is larger, and that's the ultimate strength, because if I cannot exceed the ultimate strength, the material will not start to neck and it will not start to fail. Again, when I say this, I have metals in my mind. Okay, so what I could do here is I could draw three different alloys of steel. The red one is one. The green one is another one. Okay. The blue is another one. And black is another one. Now, what we can ask is which curve is associated with the strongest steel alloy. So black is the strongest one because it has the largest ultimate tensile strength. Which one is the one that is most ductile? The blue one is the most ductile one because it has the largest strain to failure, the fracture strain. And which is the one that is the toughest? Now, that's a hard question to answer because really I need to calculate the areas under these curves and compare them. But probably the area of red and green both exceed the area of black and blue. So these two are certainly tougher compared to black and blue, but it is hard to tell which one is tougher. I wouldn't be able to do that without directly calculating the areas. Red looks like tougher, but again, I wouldn't know without calculating. Now, what is the best alloy, right? There is no best alloy. It depends on the application you're seeking. If your application is one that requires a lot of deformation to failure, this would be a good one. If it requires a lot of strength, that would be a good one. If it requires a lot of energy absorption to failure, then this is what you would like to have. Now that concept applies to metals as well, of course. You can have stronger or tougher or more ductile polymers. So for polymers as well, these concepts apply. And you may want to think about the following question. Now, suppose you'd like to build a bulletproof window, say in a bank for the teller, right? There's a guy standing on the other side of this bulletproof window. He wants to rob the bank and he has weapon, whatever, or you'd like to make a bulletproof window, right? What kind of a material would you like to use? Say it's a polymer. What kind of a polymer would you like to use? Would you like to use to make sure that it is a good bulletproof window or a surface? Would you like it to be strong or ductile or tough? Well, that's a good question to think about. Okay, so now what we would like to do is we would like to model eventually from an experimental data. Once we have the stress strain curve, we would like to extract and model the way the material behaves. And what I refer to as modeling will become more apparent when we start to talk about plasticity. But before I do that, as soon as I have any one of these stress strain curves, what I'd like to be able to do is extract some very basic information. And that basic information is the yield strength and the elastic modulus. Now, the elastic modulus, for instance, when you talk about steel alloys, the curves for different types of steel, the elastic modulus is almost the same. Again, this is a concept that you're going to see more when you take your chemistry class, and that's predominantly because the underlying material is iron. And you're adding small amounts of different materials to make that iron become steel and behave in drastically different manners after you also perhaps treat it in different ways. But because the underlying material is the same, and that's the large portion of the steel alloy, it's iron, then the curve in the elastic portion has a similar slope for all types of steel alloys. Okay. Now, however, the plastic behavior is drastically different. Failure strength is drastically different, and the onset of plasticity likewise is drastically different. In other words, the yield strength is drastically different. Here you see that probably yield strength is over here, there it's there, for red it's here, for black it's over there. So plastic behavior is drastically modified by alloying the metal in different ways. Again, same thing goes for polymers. The way you treat it will drastically alter the polymer behavior. Now, but the first thing I'd like to do is, given a curve, I'd like to be able to extract the basic piece of information, which is the Young's modulus and the yield strength. So, how do we obtain E and sigma 0 is the question that we would like to first answer. Okay, that will be the beginning point of our modeling efforts for plasticity. Now, let's go back to our prototypical stress strain curve. This is what we have. Okay, I'm trying to draw it still idealized, but as close as possible to reality. Now, because this portion is very narrow, I'm going to take that portion and zoom into it and draw that narrow portion of the stress-strain curve in a separate plot. And now, because it's narrow, when I zoom in, I am just zooming into that portion. So I magnify the x-axis. So now the slope is going to look smaller, and that is not failure. The curve will continue to increase. Okay, but I'm just drawing the zoomed portion. Now, that's the curve. There is a clear elastic region, and there is a clear deviation from that slope, and somewhere in between the plasticity must have started, right? So the question is, what is the Young's modulus, and what is that yield strength, the onset, the stress at which plasticity starts? Now, the question for E, the Young's modulus, is rather easy. Well, I identify a portion of the plot where the curve is almost linear, okay, and it will be so in the experiments. So that's that portion, and I'm going to look at the slope of that curve. Now, therefore, it is sufficient, perhaps, that I could evaluate that slope by taking a point, say that point, which clearly lies in the region where the stress-strain curve is flat. Let's call that point B, and I take the stress at point B and divide it by the strain at point B, and that would give me the slope, which is the Young's modulus. Now, that is in general not a bad idea, but it turns out when you carry out the test, this curve may not start, due to experimental reasons, may not start from zero strain at zero stress. In fact, what might happen is that this curve, when it's zero stress, it's not zero strain, but some, say, positive amount of strain. Okay, so in that region, okay, so let's zoom further. Okay, what we would like to probably see and expect is a curve that starts off like this, but in reality what might happen is that the curve starts like that. Again, this is due to experimental reasons. This might happen. So if you take this point B and calculate the slope like this, so point B is over there, what you are doing is you are taking that point, extending it to zero stress and strain, and calculating the slope. So if point B is over here, really what you would be doing is calculating the slope by let me correct that to exaggerate the error that we're making. Okay, so if point B is a point that lies on the curve, say if the point P is there, then when I calculate the slope by extrapolating to zero stress at strain, I would be estimating a slope that is less than reality. In reality, the slope is steeper. The slope I'm looking for is this one, not that one. Okay, so this is our expectation, but it may not happen. This is more close to reality. There's a tiny amount of error. This difference between 0 and a positive value of strain might be appreciable to cause significant difference in the Young's modulus. We don't know. So just to be safe, what we can do is we can take 2 points, and this is exactly what is done in the experiment as well. Eventually, the program itself spits out a stress-strain curve that eventually the data will be shared with you during the stress-strain experiment. And when the program itself calculates the Young's modulus, what it will do is it will pick a point B and a point A. And instead of calculating the Young's modulus by using only 1 point, it will actually make use of 2 points. Okay? So the difference between the strains versus the difference between the stresses, that gives you the slope or the Young's modulus. Again, why are we taking a second point? Because the curve might not be extrapolating to zero stress as strain, but actually there is some, say, positive amount of strain. If you take a single point, you would be underestimating or overestimating, for that matter, the Young's modulus. To be on the safe side, you can take 2 points, both of which lie on the stress-strain curve, and calculate the Young's modulus as such. Okay, so that's how you calculate the Young's modulus. All right, so that's fairly easy. Now there is another difficulty. Now what is the yield strength? Okay, now normally what I would prefer to do at this point is let you think about it, right? Give me opinions. But now I can share some opinions on what students have expressed in the past. So here's an opinion. Well, I will keep monitoring the slope of this curve. Okay, here it's that the slope is the Young's modulus, and what I can do is I can take successive points and monitor the slope. Okay, and when the slope changes, I can say that's where yielding happened. Okay, now that's a good idea, but that simply goes back to our idealization. Our expectation is that the curve goes straight and then there is a distinct deviation in the slope. First it has a large slope, and then there is a certain point at which the slope all of a sudden decreases. This is not necessarily something that happens in reality, but that's certainly an idea we can build upon. Now what we can do is now perhaps another idea that has been expressed is that we keep monitoring the slope, and when the deviation in the slope is appreciable enough, then we say yielding has occurred. This is an excellent idea. Okay, so we look at the slope. The slope keeps decreasing, it keeps decreasing, it keeps decreasing. Now, when that deviation, that decrease in the slope is large enough, then we say, oh, yielding must have occurred. So for instance, the slope here is like this, so the slope here is significantly smaller. I know that somewhere in between, yielding must have occurred. But the question is where, right? So in other words, how much of a deviation in the slope, how much of a decrease in the slope is large enough to say that, okay, now something must have happened. Let me call that point yielding, right? So the quantification of how appreciable that deviation is essentially the purpose of this discussion. How do we quantify how appreciable that deviation is? Now, it turns out that people have agreed on some conventions on how to identify that appreciable deviation in the slope. And one convention that people have come up with is the following. And eventually, it's a similar idea. What people have suggested is that, well, all right, so what do I know about the stress-strain curve? Now, I'm building here a little bit on your previous knowledge of plasticity from probably ME 101. And essentially what we are expecting here is that, well, I load the material, and what plasticity means for me is that when I unload, say from that point, I'm going to unload on a curve that is going to have a slope that is similar, again this is an idealization, but a slope that is similar to the slope in the original elastic portion of loading. So the slope of this line is going to be the Young's modulus. But when I hit the zero stress point, the strain is not going to be zero anymore. Well, why? Because some plasticity has occurred, right? So conceptually, when I unload, if I see some remnant, permanent deformation, permanent strain, then the material has significantly deformed. And how do I know visually that it has significantly deformed? I know that because the slope here is much smaller than the slope there. So the amount of plastic deformation that we observe, ultimately, when we unload, the amount of plastic deformation that we observe is ultimately something that is related to the extent of the decrease in the slope. So we can say now, or rephrase the question, how appreciable is the deviation in the slope, as how appreciable is this plastic deformation when I unload, right? So the slope decreases and the amount of plastic deformation increases, because if I were to unload at this point, the deviation in the slope is less, and also the amount of plastic deformation is less. So the amount of deviation is associated with the amount of plastic strain. If I unload in a portion where point B lies, which is in the elastic portion, or so I assume, then if I unload, I will go straight back to zero stress at zero strain. There is no plastic deformation. So the amount of plastic deformation that we observe is an indication of the onset of, or the extent of plasticity. So people have said, well, let us agree on a very small amount of plasticity that will be indicated as being appreciable. An appreciable amount of plasticity, so that we can be sure that plasticity has started. Okay? And that amount has been agreed to be, in most cases, as 0.2% strain. Okay. Okay, this is called the 0.2% offset, right? I'm writing the amount of strain offset as percentage. In reality, the strain itself would be 0.002, okay, which is the same as 0.2%. So what people have said is, well, if I'm in the elastic region, when I unload, I would get zero strain. If I'm significantly into the plastic region, if I unload, I would get appreciable, significant amount of plasticity. So to quantify appreciable, incursion into the plastic zone, or appreciable deviation in this slope, I'm going to assume or impose some small amount of plasticity. Okay, so I'm going to move along that curve, and when I observe a very small amount of plasticity, say 0.2%, I'm going to call that an appreciable deviation in the slope, and hence the onset of yielding. So the 0.2% offset method is used to identify the yield strength. Okay, so you start the curve, you follow it, okay, and once you identify the Young's modulus, then you start drawing a line that is parallel to it, such that that line intersects the strain axis at 0.2%, and where that red line intersects the real stress strain curve is going to be indicated as the real, or the experimental yield strength of the material. Okay, so let me again draw the same thing. So this is the stress strain curve, the zoomed portion. I'd like to identify what the Young's modulus is. That's the first step. I pick 2 points that clearly lie in the elastic region. Why 2? Because this point may not go to zero stress at zero strain. So I pick 2 points, B and A. I connect them with a line. The slope of that line is the Young's modulus. Then I'm interested in finding the yield strength. I know the slope of this line now. I draw a line that is parallel to the elastic region with slope E, and a line that intersects or starts from zero stress but at 0.2% strain, or from a strain value of 0.002, and where that line, which is not a real loading line, it's just a reference line, it's our 0.2% offset idea, where that line intersects the real stress strain curve, that's our yield strength. Okay, so that's a way to circumvent this problem with the absence of a sharp corner in the transition from the elastic to the plastic region. Okay, and this is practically important because in practice you don't see that sharp corner. Okay, so now we know how to identify the Young's modulus. We know, or we have, a characterization for the onset of appreciable plastic deformation, which is our yield strength. And now we can start to look further into the plastic region. In other words, we can start to also try to think about what happens beyond the plastic, the initial yield strength, and how to find quantities or values, parameters that quantify that plastic portion of the curve in detail. Right.